Hello students, welcome to EPG Pathshala. I am Dr. Savita Sharma from University of Delhi. Today we are going to discuss about the module Mechanical Properties Part 6 from the paper Electronic, Magnetic and Optical Properties of Materials. So students, let us see what we are going to learn in this module. In this module, we are going to learn about the plastic deformation. Then we will study about the types of dislocations. Then we will see the different modes of deformation. Then we will study about the slip systems. And in the end, we will learn about the twining. So before we start in detail, let us have a brief intro. Though plasticity by slip is the most important mechanism of plastic deformation, there are other mechanisms as well. Plastic deformation here means permanent deformation in the absence of external constraints. So in the given figure, we can see the plastic deformation in crystalline materials. The plastic deformation can be of different types. In a broader category, we have 5 major categories of the plastic deformation in crystalline materials. The first one is the slip dislocation. The second is the twining. The third plastic deformation is the phase transformation. The fourth plastic deformation is the creep mechanism. Now the creep mechanism is a broader category which includes further 3 sub-mechanisms leading to the plastic deformation in crystalline materials. The first subcategory is the grain boundary sliding. The second category is the vacancy diffusion. And the third one is the dislocation climb. Then the fifth major category or the reason for the plastic deformation is the other mechanisms, out of which the one is the grain rotation. So we have the 5 major reasons for the plastic deformation in crystalline materials. So let us start learning about what is plastic deformation. The materials may experience 2 kinds of deformation: elastic and plastic. Plastic deformation is permanent and strength and hardness are measures of a material's resistance to this deformation. On a microscopic scale, the plastic deformation corresponds to the net movement of large number of atoms in response to an applied stress. During this process, interatomic bonds must be ruptured, and then these interatomic bonds should be reformed. In crystalline solids, plastic deformation most often involves the motion of dislocations and linear crystalline defects. We know about the dislocations and we know about the crystalline defects. So the plastic deformation involves the motion of these dislocations and linear crystalline defects. Plastic deformation corresponds to the motion of large number of dislocations, and edge dislocation moves in response to a shear stress applied in a direction perpendicular to its line. So now let us study about the types of dislocations. The formation of a step on the surface of a crystal by the motion of number 1, an edge dislocation, and number 2, a screw dislocation. The motion of a screw dislocation in response to the applied shear stress is perpendicular to the stress direction. For an edge, motion is parallel to the shear stress. However, the net plastic deformation for the motion of both dislocation types is the same. The direction of motion of the mixed dislocation line is neither perpendicular nor parallel to the applied stress but lies somewhere in between. The given figure shows the formation of a step on the surface of a crystal by the motion of edge dislocation in the first figure and the formation of a step on the surface of a crystal by the motion of screw dislocation in the second part of the figure. So we are seeing the edge dislocation in the first part and the formation of step by the motion of screw dislocation in the second part of the figure. Now let us study about the relation of dislocation motion and plastic deformation. We can see the figure given below consisting of 3 parts. The first part is, which is the A part, is the extra half plane of atoms which are labeled as A. In the second part of the figure, which is the B part, the dislocation moves 1 atomic distance to the right as A links up to the lower portion of plane B. In the process, the upper portion of B becomes the extra half plane. In the third part of the figure, which is the C part, a step forms on the surface of the crystal as the extra half plane exists. So, we can note that dislocations normally move under a shear stress. We can see the edge dislocation line in the first figure with the slip plane, and we can see the unit step of slip in the third part of the figure, which is the C part. We have noted that the dislocations move under a shear stress. There are 2 modes of deformation. Number 1 is the slip and the number 2 is the twining. So let us first study about the slip, which is the first mode of deformation. Dislocations move on a certain crystallographic plane, and this plane is called as slip plane. Secondly, dislocations move in a certain crystallographic direction, and this direction is called as slip direction. Then thirdly, the combination of slip direction and slip plane is called a slip system. So the plane in which the dislocations move is the slip plane. The directions in which the dislocation move is the slip direction, and the combination of the slip direction and slip plane is called the slip system. Slip planes are normally closed packed planes, and the slip directions are normally close packed directions. In the given figure, which is consisting of two parts, A part and the B part, it is described or it is shown what are the closed packed planes and how the closed packed directions look like. We can see in the first part of the figure, which is FCC closed packed planes, and the planes are 1, 1, 1 in the curly brackets, which is depicting the closed packed planes. In the second part of the figure, which is the B part, we can see the closed packed directions, which are 1, 1, 0 in the triangular brackets. So the first one shows the closed packed planes and the second one shows the closed packed directions. Now let us study about the different slip systems. The given table describes the slip systems for face-centered cubic, that is FCC, body-centered cubic, which is BCC, and hexagonal close-packed metals, that is the HCP metals. So there are three parts. First one is for the FCC metals, second is for the BCC metals, and third one is the HCP metals. So the first category, which is the FCC metals, includes copper, aluminium, nickel, gold, and silver. And the slip plane is the 1, 1, 1 plane in the curly brackets. The slip direction is the 1, 1 bar 0 in the triangular brackets. And the number of slip systems in this case are 12. Then the second category for the slip systems is the BCC metals, which include alpha Fe, alpha iron, then tungsten, which is denoted by W, and the molybdenum, which is denoted by MO. The slip plane for these three metals is 1, 1, 0 in the curly brackets. The slip direction is the 1 bar 1, 1 in the triangular brackets, and the number of slip systems are 12. In the same category, second set of metals are alpha iron again, that is alpha Fe, and the tungsten, which is denoted by W. Here the slip plane is 2, 1, 1 in the curly brackets. The slip direction is again the same, 1 bar 1, 1 in the triangular brackets, and the number of slip systems are again 12. Then again in the same BCC category, there is a third set of metals, which are alpha iron, that is the alpha Fe, potassium, which is denoted by K. These categories are having the slip plane as 3, 2, 1 in the curly brackets. The slip direction is the same as the above two, that is the 1 bar 1, 1 in the triangular brackets, but the number of slip systems here are maximum, which are 24. Then comes the third category of the slip systems, which is hexagonal close packed metals or HCP packed. Here again, there are the three subsets of the metals. The first one is the metals like cadmium, denoted by CD, zinc, denoted by Zn, magnesium, denoted by Mg, titanium, denoted by Ti, and beryllium, denoted by Be. All these set of metals are having the slip plane 0, 0, 0, 1 in the curly brackets. They are having the slip direction 1, 1, 2 bar 0 in the triangular brackets and are having the number of slip systems to be 3. The second subset includes the metals titanium, denoted by Ti, magnesium denoted by Mg, and zirconium denoted by Zr. Here the slip plane is 1 0 1 bar 0 in the curly brackets. Slip direction is the same as the first subset, which is the 1 1 2 bar 0 in the triangular brackets, and the number of slip systems is 3. The third subset in this HCP category includes the metals titanium and magnesium, which are having the slip plane 1 0 1 bar 1 in the curly brackets, slip direction as 1 1 2 bar 0 in the triangular brackets, and having 6 slip systems. So this is the table. Plastic deformation of polycrystalline materials. So now let us study about the plastic deformation of polycrystalline materials. Deformation and slip in polycrystalline materials is somewhat more complex because of the random crystallographic orientations of the numerous grains. The direction of slip varies from one grain to another. For each, dislocation motion occurs along the slip system that has the most favorable orientation. Gross plastic deformation of a polycrystalline specimen corresponds to the comparable distortion of the individual grains by means of slip. During deformation, mechanical integrity and coherency are maintained along the grain boundaries. That is, the grain boundaries usually do not come apart or open up. As a consequence, each individual grain is constrained to some degree in the shape it may assume by its neighboring grains, the direction in which the specimen was extended. Polycrystalline metals are stronger than their single crystal equivalents, which means that greater stresses are required to initiate slip and the attendant yielding. This is to a large degree also a result of geometrical constraints that are imposed on the grains during deformation. Even though a single grain may be favorably oriented with the applied stress for slip, it cannot deform until the adjacent and less favorably oriented grains are capable of slip also. This requires a higher applied stress level. So students, let us now learn about twining. Twining is a shear force which can produce atomic displacements such that on one side of a plane, which is the twin boundary, atoms are located in mirror image positions of atoms on the other side. That is, the twining is a kind of force or a kind of shear force which produces atomic displacements on the side of the plane such that atoms are located in mirror image positions with that of the atoms on the other side of the plane. It basically leads to the atomic displacements. Then, twining is common in hexagonal closed pack structure and body-centered structure. That is, it is common in HCP and BCC structures. Twining leads to limited deformation, but it helps in plastic deformation in hexagonal closed pack and body-centered crystals. Meaning, despite of having limited deformation, it helps in plastic deformation in HCP and BCC crystals. Twining occurs on specific twining planes and twining directions. That is, the twining has specific planes to occur and particular directions on which it occurs. Here figure consisting of two parts A and B is the schematic diagram showing how twining results from an applied shear stress. These two figures shows the twining resulting from the shear stress. In the second figure, that is in the B part, open circles represent atoms that did not change position, while the dashed and the solid circles represent original and final atom positions respectively. In the first figure, we can see the polished surface and the direction of the applied shear stress. And in the second figure, we again see the another type of twining which is resulting from the applied shear stress. Now let us compare the slip and the twining. The first difference between the slip and twining is the slip is homogeneous while the twining is more localized. Secondly, the slip is common in face-centered cubic type materials, while the twining is common in hexagonal closed packing and body-centered cubic packings. The third comparison between slip and twining is that slip occurs under static loading, while the twining occurs under shock loading. So students, let us summarize what we have learned in this module. From this module, we should be able to define about the plastic deformation and slip systems. That means we have learnt about the plastic deformation slip systems. We have also learnt about the slip in single crystals, the plastic deformation of polycrystalline materials, and in the end, we have studied about the deformation by twining. In addition to these, we have also learnt in short and we have the quite well understanding about the twining, about the slip, about the systems of slip and the factors affecting the twining and the planes and the direction in which twining occurs. Thank you.